Okay, so to finish what I have shown yesterday about the VEMOS project, first I will show you a big experiment that has been done last September. So we have a big boat inside the boat from Ifremer, in the middle of the Atlantic Ocean, and here is VEMOS. So here VEMOS is working. I mean, he is supposed to take measurement inside the sea. The control has already been tested. Now, VEMOS has to do his job. So here on this video, we see just the beginning of the mission. Put it inside the water, and it will go for a mission of 3 days. Of course, at the moment, it is almost autonomous. We'll start the program, and after the guy come back to the big boat of Ifremer, and the boat start its mission. Yes?
I just want to know what are the sensors that you're using. So I know from yesterday you said you are using a wind sensor.
Yes, wind sensor.
How do you know where you are at any point?
GPS, of course.
Ah, so you have a GPS.
Because it's outdoor, it's not underwater.
No, you have a
GPS. So here there is no problem of state estimation. It's only a control problem. 3 days after, the robot is coming back. So what I wanted to show you is just how we put it inside the water, what is the operational mode, and also to come back here. Excuse me, that's what I wanted to show. Okay, it is what VEMOS has done during its mission of 3 days. So it starts here. It has to scan a zone like this. Of course, we have the feeling, because it's a zoom out, that it is perfect, but if you zoom in, it's not totally perfect. Here it's something like 20 kilometers. The whole trajectory is something like 300 kilometers. When the robot has finished its mission, then the pilot of the boat said, oh, you have to, so here he has finished. So first, it has to come back. But the pilot of the boat said, oh, maybe it's better if it waits here. So we put a triangle. And the boat is doing triangle several times. 10 times, 20 times, whatever. So here you maybe have a few kilometers. After, the pilot of the boat changed his mind and said, oh, it's better if he could wait here. So he made some squares. And so that's why you should understand this geometric shape as VEMOS is waiting. Okay, just to illustrate that the control is, can be considered as operation. That's all for the lesson of about the sailboat control. Now, so what I will do today. So today we can ask questions. We can do exercises. I will try to help you to implement, if you want, C++ code with interval libraries, for instance. So what I suggest for interval libraries is, so I have a very simple example with few lines of code where you can implement your own C. What I propose, which is what we do, we use C++, the environment, and we use Qt Creator. Whoop. Okay. Okay, Qt.
Maybe you can change
Yes.
the color of the...
Maybe I will try different. Okay. So what we use is, okay.
Yeah,
Qt Creator. Why? Because it can work on Macintosh, on Linux, Windows. It's a multi-platform environment. And of course, it is C++. Very free. It's what we use. So it's free. And I can explain you how to implement it. Then, a more efficient way to implement it is to use IBEX. IBEX is a contractor libraries made by Gilles Chabert in Nantes. There is a team. We try to participate to the IBEX project, and you have there very efficient contractors. So you Google IBEX 2.0 and you immediately find some tutorials. Okay? Now, what I suggest is to start with something like half an hour lesson about nonlinear control, because I know that in your lab it is the case here. Also, you work with nonlinear control, maybe most of you.
I'm doing UAVs, so my side is not
AUVs?
unmanned aerial vehicles.
Area vehicles.
Okay, I have it. Okay.
Yeah, but non-linear
Okay.
also.
We're not working on the low-level control side, we're doing the high-level one. So I will be dealing later with cost functions and
What high level?
What kind of
What high level is like what?
Plan
mission
definition.
planning.
So
Okay.
path control, path planning, control,
Yeah.
stuff like that.
Okay, so some of the concepts will be useful.
Yeah, especially the contractors and the interval computation.
Yes.
Because what we're looking into doing is having more than one UAV
Okay.
and having more than one mission, and then you need to optimize the way that would deal with it. So
Okay, nice. Swarm of robots.
like swarm of robots, but not going to do one mission,
Yes.
rather than you have a set of missions and then.
Okay.
Which group are you in?
Sorry.
Which group are you in?
You married?
Sorry?
Are you working with Alexander Lanzon or which group?
I'm not the mix.
Mate.
UAV research group
Oh,
with
mechanical.
William Crowder,
Mechanical.
aerospace.
Aerospace group is
okay.
you marry or something, no? You are married.
It's in here in Manchester, right?
Yes.
Okay, so
There's Bill Crowder, and the head of the group is William Crowder
Oh, okay.
and Peter Horwood.
And for
We're doing with Alexander Lanzon a part of the project.
Okay, so I will say a few words about nonlinear control, and I wanted to speak about two things. First of all, again the same, but not in the same way as we did different. So I wanted first to present you a sailboat model. So of course you do not have to understand all this equation. It is a simplified sailboat model. So I remove a lot of coefficients. It's an approximation. But you can see here x and y, the position of the robot, theta, the heading, the angle of the sail, the angle of the rudder, the speed of the boat, the angular velocity of the boat, the force on the sail, the force on the rudder. So it's a complicated, I would say, state equation. The corresponding, excuse me, the corresponding state equation can be seen in the simulator. I have shown yesterday. Just have to find it. I don't find it here. Maybe. Yes. Here. You can see it was this one. You know, I remember, I turned the rudder. So, it is the corresponding behavior of the rudder. So, it's an approximation of what could appear in practice. You can see the inputs. The inputs are U1 and U2 correspond to the angle of the sail and the angle of the rudder. So whatever, you can see that it is nonlinear. Now, what I want to explain you.
Sorry, can you say again? Two inputs and what is the inputs here?
The inputs, so the input is the angle of the rudder
Okay.
and the maximum angle of the sail.
Okay.
Where are they here? Which one?
It's you.
So
you want to
the same.
Okay, okay.
V like voile in French, J like gouvernail, rudder. Okay.
So
Sorry.
here we have a disturbance also, or no?
No, no, no,
No
not this one. No, no,
disturbance.
no, no. And it's also an approximation of the model, but just to so that you can see that it's moving around. Most of the time we use more complicated model, but I can.
This is
Here you have no coefficient, for example. It's a normalized model. Just so what I want to say is you have state equation like this one, and you have an output, which what we call output is the desired output. We want to control, it corresponds to the variables we want to control. GFS. We have something like this. Now, so we don't speak about sensor. With a sailboat, we are able to measure everything. We are able to measure the direction of the wind, the speed of the robot, the position, the angle of the sail. We do not have for the sailboat a state estimation problem, only a control problem. So y corresponds to the variable we want to control. So now, what is important in practice on the sailboat, what we want to control? We want to control the heading, theta corresponds to the heading of the robot, and the speed, EI, desired output. So, if we want a given heading and a given V, or given Y, we have to solve. Some output would be possible, some will not be possible. So we define the set of all acceptable output, Y, as the set of all Y, such that Y equal G of X, of course, but also X dot equals 0, so that I can stabilize the system on the ground. So it means that f of x u equals 0. To be rigorous, I should have inserted here such that there exists u such that f of f xu equals 0. What we have here, it's not a differential equation, it is equations. I have a set of equations and I will project on the y space. Understand? So, I have here y, which is unknown. Here I have u and I have x. I have equation, and I will compute this projection. Okay. It is a set of all acceptable important problems in control theory. What, in our problem, what is y? It is theta and v. If I draw it, as I explained, this, which is exactly what I have explained here, solve it, except that I have removed the two first equations, because I don't want x and y to be constant. I want the robot move. So I remove the two first equations, and f does not take anymore x and y into account. And I will obtain what we call a polar speed diagram. What is a polar speed diagram? Polar speed diagram is a polar view of all heading and the corresponding speed corresponding that are acceptable. The notion of polar speed diagram is exactly corresponds to the acceptable output. Okay, in this particular case. So let me show you in practice how what it represents. So this has been made by Pau Herrero, which is now in
England.
In England, yes, in the Imperial College,
Yeah.
when he was in PhD. So here it is a set of output. Let me click here. it means that I choose this speed and this heading. Then what will happen? The interval method will solve this equation and will find the corresponding u. If I have some kind of stability, then the desired output will be satisfied. So if I consider other output, you can see here I have some other desired output. I click here, I click here, I will click here, up, and you can see the robot control its trajectory so that it will respect the set of feasible desired output. Okay? So why interval analysis is needed? Yeah. It has been needed to characterize the set of feasible desired output, but it is also needed at each time I change the desired output. It is also needed to solve this system of analytic expression to find the right u. Okay? So as you can see, these singularities cannot be crossed. If I click outside, you will have no solution. And the control will not work, of course.
For instance, you can obtain a set of views, no? For some.
Well, if I choose this one,
Yeah.
there is no corresponding control.
No, but I mean, you obtain a set in U, not only one U.
Ah, okay, but you choose one.
Yeah.
It depends. When I am on the frontier, most of the time there is only one.
Yeah.
But look, if I click here, which corresponds to a low speed, you can have two solutions. So it takes one.
Yeah.
But it takes one, but it corresponds, this one, to a bad tuning of the robot. Because most of the time, when you pilot your sailboat, you are always on the frontier. You try to go as fast as possible. Here, I don't try to go as fast as possible. So there is different bad tuning, but there is only one good tuning to go as fast as possible. Everything has to be optimized. It's okay?
Yeah.
So it was the first application to show you a nonlinear control problem, where I can be, and with the notion of acceptable desired output. Okay? It was my first application I wanted to speak today. Again, if you have any question, speak diagram. Later, we'll discuss about the, how we call it, I don't remember. When you want to fix in your boat inside the zone. So here I want the boat to stay inside the circle. I will speak it about later, so I have forgotten the station keeping problem. Call it the station keeping. We have a sailboat. We are inside the ocean, and we wanted to sail inside a disk with a diameter of 10 meters. Station keeping problem. To behave like people. Doesn't have to be. Okay, so what else? I wanted to show also that we can combine the approach I have described before with a set of all acceptable, to think not anymore with dynamic equation, because here the differential equation do not appear anymore, but we can combine this approach to transform the problem of motion planning, which takes into account the differential equation, into a path planning problem, where the robot has to go from one point to another, but without taking into account the differential equation. So it's easy after, much more easy without the differential equation, to find a path from one point to another, to park your boat, for instance, inside a harbor. It's okay?
But the set of solutions that you got are set
This one.
Yeah, the red ones are the possible inputs, the possible feasible inputs.
The what we call the desired output. the set it corresponds to the set of all feasible heading and speed, you can go with your boat in a permanent mode, not in a transient mode. Okay? Yeah. And then you can think with this, not exactly with this, but with the convex hull of this, in order to do your path planning, to solve your path planning problem. But your motion planning problem becomes a path planning problem. It means that you can move your boat without thinking to its dynamic. Okay? Yeah. So I will stop with this. And the last application I wanted to illustrate today is the notion of attractors. So I consider here a system. F of x, no more control. The control is inside. So remember, you have a robot with different control. As soon as you put inside a controller, your system becomes autonomous and is described by such. When you have uncertainty, of course, it becomes a differential inclusion. But here, for simplicity, I will, if the problem is already complicated enough, to we only consider this kind of system. Okay? But it will be totally non-linear. It's already complicated. So what is an attractor? If I draw here x1, x2, the state space, if I start with the point, I simulate, I can converge to a limit cycle. So limit cycle is an attractor. Okay? Equilibrium point is also an attractor. A point which is unstable is not an attractor, but it belongs to the limit set. It's a limit set. So we have a limit when t tends to infinity, what we call omega limit set, the last letter of Greek alphabet, or alpha limit set when t goes to minus infinity. But they are considered as limit sets. What we consider here is the characterization of limit sets of a system described by nonlinear equation. So I think that interval analysis is a very good tool for this. It has been proved by Warwick Tucker in 2001, where he has proven that the Lorentz attractor was a strange attractor. So it's a very strong result, and it was impossible to obtain such result without interval analysis. So the idea is to use the ideas of Warwick Tucker, some ideas, and to apply to robotics. It is the idea. So, first of all, I have a system, what I call a limit set. So limit set is what I have defined. I have the solution with respect to the state. So phi is a flow function. It means that if I am at x at time 0, at time t, I will be at position phi of tx. So what is a limit set? It is a set of all x such that for all epsilon, epsilon is small, there exists a t bigger than 1, or maybe anything else, such that one day I will come back here. But it should be true for all epsilon. It is a definition of what we call a limit set. An attractor is a limit set, but not all limit sets are attractors. But I will consider only limit set. I put attractor for sure at the beginning, but most of the time it's quite easy to get rid of unstable limit set.
So what you mean is all attractive limit sets are stable.
For instance, if I have an unstable point, it is a limit set because if I take a small epsilon here, if I start here, I will stay here. So it belongs to a limit set.
What I meant is all attractive limit sets are stable. If it's
All,
not attractive, it's
so
not
all
stable.
attractors are limit set
Okay, and they are stable.
and they are stable.
If it's not attractive, it's not stable.
If it is a limit set and it is not an attractor, it means that it is not stable.
Okay.
Okay? Okay, sorry. So, what is the idea of what we want to do? So the idea is the following. We have the state space, x1, x2, and the idea is to discretize it. But not discretize with time, discretize with space. It is what we call a quantization. So, we quantize with polygons. Okay? It is a quantization. So here, it will correspond to one element of a graph. So, this polygon here will correspond later to a node of a graph. Here you have another one, it will correspond to the node of a graph. I will have several nodes, and I will try to put relation between the nodes. And I will define now what I mean by relation between the nodes.
So
Okay.
cell decomposition.
Yes, yes, cell decomposition. It's okay? Good. So it is the idea. First of all, the decomposition, the cell decomposition, I will call it a set of non-overlapping polytope of orbit. It's a set. Okay? The union should be equal to Rn, but also I ask that I have no overlapping. It's okay? Okay, so what is the relation? Difficult to explain here, but I will try to do. If there exists, if I am here, I am in the polytope number E. It is here the polytope number E. I have a trajectory, and this trajectory for one t, so here it's t equals 0, for one t, it will go out of the polytope. The time at which it go out is called eta of x0. The time at which it goes. If you never go out, because for instance you have a limit zero, eta of x0 equal to five convention
Zero set.
to
The
Empty set.
empty set.
no, it's not a set, it's a point, you know, it's a t, at which the first t,
Infinity.
Oh, infinity.
infinity, yes, it's a convention, which is quite natural, it's a convention. Okay, so let's see what is in here, I have, now I will propose the following relation. If for all, if there exists a trajectory such that from number E I go to number G, then I will say these two polytopes have a relation. The relation is denoted by this. So the polytope X will be in relation with this one if there exists a common frontier. Okay, common frontier means this, a common intersection, and there exists an initial condition such that I will go from here to here. It is a relation I propose. So of course I will illustrate. The definition is quite formal, but I illustrated here. I have some kind of vector field here, and if all vectors go like this, I can say that first, in this example, that XE is not in relation with XE because of the definition, which is I will never stay inside. So for infinity, if I start here, eta will be equal to infinity, and when eta will go to infinity, I cannot be inside XE, so I will say, by convention, XE is not in relation with XE. We'll understand better for the second example. This polytope is in relation with this one is not in relation with this one. You understand? Okay. Now here, this one is in relation with this one is also in relation with this one. Okay. So what is important? To have as few arcs as possible. An arc is not very informative, the absence of arc is an information. Okay? Okay, follow? So now, how can I prove it? With interval analysis, I first have a guess which n, which corresponds to the perpendicular of the frontier. And I can check, using contractor approach, that all the arrows of the field have a positive scalar product with n. In this case, I can show that this one cannot be in relation with this one because one trajectory, otherwise one trajectory would cross the frontier in this, with this direction. It's okay for you? How to prove it? I will not explain how to prove it, but you should understand that at this step, interval analysis is needed. Okay? You can prove it with this relation. So, what is a quantization? What I call a quantization? So maybe there is better, if you know better name, please suggest me. But it's a graph. Not only the decomposition, but the graph. So it's a kind of discretization of the state equation. I had a state equation like this one, and now I have a graph. I will explain earlier on a simple problem, which is a station keeping. Station keeping, I will start with this simple non-autonomous system, which is written here. So, roboticians love this system because simple to write, a long time to. It's a, you know the system. This system, so x dot equal cos theta. So I write it because it is small, and we have time to think. So it corresponds to the sim wave robot. Okay, theta is a heading. And first question: is it possible for this robot to stop?
No, velocity is always one.
The velocity is always equal to 1. Always equal to 1. Exactly. It cannot stop. Like a sailboat. A sailboat cannot stop. You can prove it, it cannot stop, except if you have no wind. But if you have wind, the sailboat can stop. So the idea is a sailboat. You cannot stop, but you want your sailboat stay here exactly. Exactly means 10 meters. Okay. So here, I want the robot goes here. Of course, it will not be able to stop, but it will turn around this one. But what I want to do is to give a circle. And on this circle, I want to prove that it will stay forever inside. So what I want to do is to prove that it is not inside. One day, it will enter in the disk, and after, when it will be in the disk, it will stay there forever. But I cannot find control for that. Why? Because if my robot is just here with the bad direction, it will get out. So we cannot think in a two-dimensional Okay, but we want something rather automatic, so it will be difficult to propose a shape, of course, if you find it. But the shape is not so easy to find. First of all, in this example, so I have chosen this example to, you should understand that my problem has some kind of symmetry. There is, this problem has a symmetry of rotation. I mean, if I am here, or if I am here, or if I am here, it's the same. Okay, what is important? If I turn the plane like this, so my problem has a symmetry of rotation. You understand? If this one, if I put this one, maybe my picture is not so good, but if I am in this position, or in this position, or in this position, with respect to 0, I am exactly in the same, yes, I have to apply the same control.
You don't care about the orientation.
It is not, I don't, I mean, if, it's not me who care or not, it is the problem if you have a good algorithm, I don't know the algorithm, but the best algorithm to solve the problem, if you are in this position or in this position, you will apply the same control. The strategy will be the same. Okay, so this problem has a symmetry of rotation, a cylindric symmetry. It's okay for, so in this case, the first thing you have to do is to make appear in your state variable this rotation variable. So to change your state variables by homomorphism in order to make appear the symmetry variable. So of course I propose here a new variable alpha. The state where x, y, and theta, now the states are alpha, d, and phi. So, you understand? I will, so it's a polar coordinate, Cartesian coordinates. So this step is important. Why? You will understand why? Because if I change the coordinates, I will obtain new state equation. With phi, d is the distance, alpha, descent. D is the distance, and phi corresponds to something like this. Okay. Now, what is important, and we can see the symmetric problem, is that alpha dot depends on phi and d, of course. But here, you have no alpha, no alpha. Since you have no alpha, the dynamic of phi and d does not depend on this equation, and this equation can be removed. It's okay. So, it's important because my problem is now a two-dimensional problem. And in a two-dimensional problem, I can draw things.
But this trick only works in this problem.
Yes, of course.
It doesn't work in...
No, of course. Because the idea is to develop a general method, but the general method should, because this problem is complicated in engineering. But you should illustrate on a simple example to understand it. So that's why I try to find good two-dimensional examples that are not so simple to solve, but even in a two-dimensional problem, you will see that it is not easy. So, the strategy I propose. It's okay. So, of course, the strategy I propose will be the following. If I am in this position, should I turn right or left? Let's try to propose a strategy. Turn right or left? So we turn right. So the strategy we can propose is, if we are here, we turn left. If we are in this position, we turn right. First position. And if I go towards 0, I will perform a proportional control. I am guaranteed to converge here? No. Of course, if I am exactly like this, I will go this direction. A small perturbation will make it work. I will go here. Everything's perfectly like this. And here, of course, I will go like this, but a small perturbation will be made here. I can make some tests. It will work perfectly, but mathematically, it's not proven. And one day, I will build thousands of robots. I will build millions of robots. People will start using it. And one day, we'll have an accident, and we'll see that it is because the case that never appear with a probability almost zero. And so we want to prove the strategy is not good. So the strategy proposed is the following. If my robot...
But you can always add an if statement for the zero position.
I can always
add an if statement for the zero position. So if you are at zero and pointing outwards,
of course,
then you pick right to left.
Yes, of course. But if I am here, what should I do?
Yeah, you're pointing out of zero.
Yes.
So you are at the 0 degree angle. So
yeah.
Pick one.
So I turn like this.
Yes.
If I am like this.
So you induce.
I turn left.
You induce your perturbation.
Yes. So if I like this, should I turn left or not?
Yes.
So if I turn left, I will come back, and one day I will be like this, exactly on zero.
Yes, but you also know which direction you're pointing, don't you?
Yes, you know.
So if you're going towards zero.
Yes, exactly.
Yeah.
But if I move epsilon, I will not be exactly towards zero.
But you said if you are pointing to zero, you do a proportional control.
Ah, okay. So what means towards zero? There is some kind of inequality. Yes. I think you're right. So what I suggest, maybe it will be similar to what you propose. We'll see. Now, sorry, like this. So, a lot of robots. Swarm of robots. So, the strategy is, if my robot, which is here, is points towards zero inside with a given precision, this, for instance, if zero is like, so I have a robot, I have a cone, let's say plus minus p divided by 4. Okay. If zero is inside this cone, proportional control. If I am out, I turn it. You understand my strategy? I want to go to zero. If I am like this, zero is here, proportional control.
Okay.
If I am like this, I turn left, so that I am.
Okay.
Is it sure that I will converge towards zero? No? Sorry? No, just to show you that even here it's not evident to find one. That's what I want to do. It's a station. What I propose is this one. So smaller than this one, so it corresponds to an angle of p divided by 4. Then I turn left, otherwise a proportional control. So I tried, of course, to find simple equations to we are in the academic world, so I try to avoid coefficients and so on. It is a proportional. It's okay? Now, I have an autonomous system. There is no more U. We have an autonomous system of this form. Now, this system is not continuous. Of course, there is a theorem, bracket theorem, that tells you something like you cannot control with this type of problem. You cannot find a continuous control. There is a theorem like this. That we put 20 years ago. Bracket theorem. Okay, so in fact, when I put U, as I said, I obtain this system, which is not continuous, the control is not continuous. Then, this system, there is only two variables, and I can draw it. So let me draw it. Oh, let me illustrate it first. I start here. I do not towards 0. I turn left. Up. I go directly towards 0. Then after, of course, my angle is bad again. I turn left, and I will converge to some circle in not single way. If I add some noise, then I will move everywhere. Will I stay always here? By simulation, impossible to prove it. How can I prove it? So, first idea is to draw the vector field. Here you have the vector field. It's not so infinite. So, you understand that here you have phi between minus p plus p. So the state space is not a plane, it's a cylinder. So this point is the same as this one. You understand? Okay. Now, if I start here, you see, previous slide, you can see here a simulation. I turn left. I turn left means theta is increasing. Theta, phi is increasing. Okay? When I am here, I am here. Phi is increasing. Here, it is a distance. The distance here stop increasing. Sorry. So it means that I am here. The distance stop increasing and will decrease. It will decrease and I will be at 3. Up, will decrease, and I will go here. The distance will decrease. And there is some kind of, I cannot explain exactly what will happen here, but there is some, the robot will turn like this in an unstable way, and maybe it can go here. Okay, so now what we want to do is to prove that if I start from far, I want a circle where I am sure that the robot will converge. That's the problem. So, I propose this decomposition.
So we cannot conclude anything from this diagram about this type of
Not yet. We will, but not
now. We
not yet. We can see that. I think we can see things. For instance, the idea is here. No. If I take a trajectory here, I can understand that I will go here, I will go here, I will go there, and I will go. Maybe I will do something like this. And if we can understand that we converge this region. Go.
Yeah, you will be there somewhere in that way. You will not go outside.
Yes, you can understand that you will not go outside. So how we do in practice? So we have to compute that automatically.
Or at least we need to know what is the maximum we can converge.
Yes.
Because it's obvious that they are somewhere.
Yes.
If you are inside, you will never go out.
Yes. So a possibility would be to start with a lot of simulations, a lot of initial conditions, and to see what happened, but we want a proof. Okay.
Sorry. You said if we are in the right side this circle, it's okay that if it's not in the between the minus 45, turn left. But when we are in the left side of the circle, in the minus part, we have to turn right. And this shows that we turn right.
If I am here, if my robot is here.
No, if you're a robot in the left side, in the
Here.
minus part, yes,
Here.
you have to turn.
No. If I am here, for instance, like this. If I am like this, or like this, it's the same.
But in this picture, the sign shows that it comes to right, it's not.
Here.
know that part.
X3.
Yes, here, yes, for example, see, all of these signs turn right,
Yes.
not turn left.
Yes, all go to the right.
Okay, but you said that you have to turn left. So how you change these roads?
Ah, but no. Excuse me. When I say I turn left, it means that phi or theta increases.
Okay. Oh, okay.
So when
the
it increases,
minus-
it goes to the right.
Okay, I get it. Because it's a minus. Okay. Okay.
Okay. So go to the left. In practice, in the trigonometric direct sense, means when you go to the left, your heading is increasing.
Okay.
When it is increasing, here, you go to the right. So I understand.
What's that?
Okay, so what will we do here? Is we'll build the decomposition and we'll do some kind of curve. So it's quite easy to see, because when you are here, you know that there is some trajectory. Excuse me, the laser is not here. Oh, okay, thank you. So, there is some trajectory starting here and go here. So x1 is in relation with x2. Okay. x2 is not in relation with x1. Because if I am here, at the moment when I will go out, I will not go to x1. There is no trajectory going that way. Okay? So x2 is not in relation with x1. Of course,